Continuing with our discussion of formal proofs of limits, we now consider limits at infinity. So we say that the limit as x goes to infinity of f of x is equal to L if for every epsilon greater than 0, there is an m dependent upon epsilon such that x bigger than n implies that the absolute value of f of x minus L is less than epsilon. So another way of looking at it is that it doesn't matter how f of x is behaving before m, but once you get to m, or you take any x past m, then the values of f of x are within epsilon of L. Okay? Similarly, for limits at minus infinity, the limit as x goes to minus infinity of f of x equals L means that for every epsilon greater than 0, there exists an m dependent upon epsilon, such that x less than m implies f of x minus L is less than epsilon. So it doesn't matter how f of x is behaving before x equals m. Once you're to the left of m, then you're guaranteed, once x is to the left of m, you're guaranteed that f of x is within epsilon of L. Okay? So for example, I claim that the limit as x goes to infinity of 1 over 2x plus 5 is equal to 0. It seems intuitively obvious 2x plus 5 gets arbitrarily large as x goes to infinity, and then 1 over that gets arbitrarily small. Okay, so let's try a proof. I want to find an m such that when x is bigger than that m, then f of x will be within epsilon of 0. Okay. So I want to consider 1 over 2x plus absolute of 1 over 2x plus 5 minus the claimed limit, which is 0. Okay. Now I can drop the 0, so I just need absolute 1 over 2x plus 5 to be less than epsilon. Now when I take the reciprocal, then I have to remember to flip the inequality. So absolute of 1 over 2x plus 5 is less than epsilon if and only if absolute of 2x plus 5 is greater than 1 over epsilon. Now, we're taking x going to positive infinity, so we're going to be considering positive numbers. Okay, so I can drop the absolute value sign. So now 1 over 2x plus 5 will be less than epsilon if and only if 2x plus 5 is greater than 1 over epsilon. Okay, then I can take the 5 over to the other side of the inequality. That would leave me with 2x is greater than 1 over epsilon minus 5. And then I can divide by 2. That would leave me with x is greater than 1 over epsilon minus 5 divided by 2. So now I have my m. So I can run this algebra backwards, and I can say that when x is greater than 1 over epsilon minus 5 over 2, then the absolute value of 1 over 2x plus 5 minus 0 is less than epsilon. Okay, so if we set m is equal to 1 over epsilon minus 5 divided by 2, then x greater than that m implies that the absolute value of 1 over 2x plus 5 minus the claimed limit 0 will be less than epsilon. Okay, so that concludes our discussion of formal limits, and I've covered some material which is maybe a bit too advanced for this course. I would expect you to be able to do something like do a formal limit of, say, a monomial function using the epsilon delta approach. I wouldn't expect you to be able to, or to do a limit at infinity like the one we've just done. I would not expect you to be able to do something like uh, prove something about the composition of arbitrary functions.